How to determine the number and size of required exits. We're talking all about exiting in this series. What about how many exits? How large do they need to be? The number of required exits is primarily driven by the number of occupants. As a general rule, all buildings must have 2 exits. Buildings with a high occupant load require a 3rd exit. Buildings with a really high occupant load require a 4th exit, or possibly more. To a lesser degree, the number of required exits can also be influenced by the layout of the building, particularly the path of travel of occupants. We'll touch on this briefly towards the end of the segment. Primarily, we'll focus on the number of occupants. Where the story of a building has between 1 and 500 occupants, 2 exits are required. Where the story has 501 to 1,000 occupants, 3 exits are required. Where the story exceeds 1,000 occupants, 4 exits are required. In the IBC, we'll find this by going to Chapter 10, then Section 1006, subsection 1006.3.3, and finally, Table 1006.3.3. In NFPA 101, we find this by going to Chapter 7, then Section 7.4, subsection 7.4.1, and finally, Section 7.4.1.1 and 7.4.1.2. Now, there are exceptions to this, which we'll get into later, but this is the most basic and fundamental requirement. Why? Because more people means more exits are required. The number of exits and the width of exits, which we'll touch on soon, are proportional to the number of people. No, why 500? That seems awfully arbitrary. Well, this again is the case of rule of thumb. Remember, these building codes date back over 100 years, well before something like computational fluid dynamics and computer-based egress simulations were feasible. Could you do some modeling with today's software capabilities to prove that you can safely egress, say, 632 occupants on the floor of your designed building safely before conditions become unsafe, including a generous safety factor? You could. This would require the use of the alternative methods provision in the building code, but that's a heavy computational requirement, and there's no guarantee the modeling is going to give you the results you desire. In fact, it might say you need a 3rd or even a 4th exit. There's also the difficulty of familiarizing the AHJ with this method and getting them knowledgeable and comfortable with your analysis to approve your alternative method. It's probably just easier to add a 3rd exit. Sure, I get that, but how do we know that 2 exits is safe for 500 occupants, or 3 is safe for 1,000? Well, there are hundreds of thousands of buildings built to these standards. Generally, these buildings are safe, and in the decades that have passed since their construction, fire tragedies and losses of life have not challenged these requirements or proven them unsafe. Remember, codes change all the time. They evolve with technology, cultural changes, and changes in building uses. Exterior building combustibility, lithium-ion batteries, wildland-urban interface. These areas of the code have changed dramatically in recent years. One area that hasn't changed is minimum number of exits, because historically it has worked. If at some point it stops working, codes will evolve accordingly. What if I have a really big exit? Can't that accommodate a whole lot more people than a small one? It sure can. This is where occupant load factor comes into play. Before we jump into that, I want to discuss a code concept that somewhat restricts the idea of having one huge exit to make up for other exits being undersized. Where only 2 exits are provided, the exits should be equally sized. That's not actually a requirement, but is a good simplification. The concept is that if one exit is unavailable, we need the other exit to accommodate the occupants. Now, don't go thinking we need to size that second exit for the entire occupant load. We don't. We distribute occupant loads equally amongst exits. But back to the question, why not have one very large exit? Let's say in this scenario, I lose my really small exit. No problem. We have that huge exit. That can take a whole lot of people. Yeah, but what if I lose the big exit? Well, now the remaining smaller exit is undersized for the occupant load. It can't handle the volume of people. That's why we have a provision in code addressing the distribution of exit capacity. The code says that one exit cannot account for more than 50% of the required exit capacity of the floor. This shows up in the IBC section 1005.5 and NFPA 101 section 7.3.1.1.2. Meaning if I size my exits equally, that's 50% exactly, and I meet this requirement. If I have disproportionately sized exits, this means that the bigger exit doesn't actually help for egress purposes. It's still an exit, but that extra width doesn't do anything for exit capacity. The more restrictive, the smaller exit would govern. More specifically, computationally, 2 times the width of the smaller exit would be the allowable exit capacity. If there are 3 exits, the 50% rule still applies, but you could theoretically have 1 larger exit and 2 smaller exits that add up to the size of the larger exit. So long as that large exit is not more than 50% of the required capacity, this is allowed. However, if we want to keep things simple, we can assume that all exits need to be equally sized, and if they aren't, one exit is not permitted to take more than 50% of the occupant load of a floor. Does the size of an exit impact the number of people that can go through them? Yes, the size of exits affects the number of people that can go through them. How do we calculate this? Using a concept called exit capacity factor. Bigger exits mean more people can go through. If you recall the concept of occupant load factor from previous videos, the way we knew how many people were in a room or space was dividing the room's area by its occupant load factor. Similarly, by taking the width of the exit and dividing it by the exit capacity factor, we can determine the number of occupants the exit is capable of handling. This is true for all exits. For interior exit stairs in particular, both the width of the door to the stair and the width of the stairs themselves must be analyzed. The basic premise is, if you have a lot of people, you need wider exits. If you have fewer people, your exits can be narrower. How do we validate exit capacity? How do we assign where occupants go? The simplest approach for validating exit capacity is to take the occupant load and divide it by the number of exits. Then assign occupant loads to each exit equally. That's our basic premise and a good general practice. The code language requirements are only slightly different. In IBC section 10.05.3 or NFPA 101 section 7.3.1.1.1, the requirement is that the number of occupants cannot exceed the total capacity of all available exits. And, as we previously discussed, no single exit can provide more than 50% of the required occupant load. So, theoretically, you could have exits of different sizes, and each exit could be maxed out with occupants. Assuming all exits are available to all occupants, and no single one of those exits is more than 50% of the required capacity, this would comply. My recommendation, first divide the occupant load by the number of exits and see if there's enough capacity. If this works, you're good. The more complex method is technically correct, but I would only use that if the first method doesn't work out. Now, why did I add the caveat available to all occupants before? Well, just because there's a door to the outside, it doesn't mean that it's an exit for all occupants. Consider a fire pump room with only one exterior set of doors. The only way in or out of that room is through that exterior door. That exterior door is an exit, true, but it's only an exit for the occupants within the fire pump room. You would be incorrect in counting that as one of the exits if you took the whole floor plan's occupant loads and divided it by the number of exits. Why? Because occupants elsewhere in the building cannot use the fire pump room as a way to get out. Another scenario is if the building is subdivided into tenant suites, or if there is a locking arrangement which would permit only certain occupants from using certain exits. In these cases, you would break up the floor into chunks. Let's say it's a 2-tenant building. There's a central core with 2 exit doors. Additionally, tenant A has its own exit door. Tenant B does not have its own exit door and does not have access to tenant A's space. In this case, tenant A has access to 3 exits. Tenant B has access to 2 exits, and the lobby occupants also have access to 2 exits. The same methods described above apply. You can divide the number of occupants by the number of exits available to those occupants, equal distribution. This is the simplest approach. If you use equal distribution, divide tenant A's occupant load by 3 and distribute them amongst the 3 exits. Divide tenant B's occupant load by 2, because they only have access to 2 exits, and distribute them amongst the 2 available. Then divide the lobby space by 2 and distribute them among the 2 available exits. For the door out of tenant A, this would be 1/3 of tenant A's occupant load. For one door out of the lobby, it would be 1/3 of tenant A plus 1/2 of tenant B plus 1/2 of the lobby. The second lobby exit would have the same value and calculation. Alternatively, you could max out each exit, but only to the extent exits are available to each occupant. You cannot have tenant B or lobby occupants exiting through tenant A. Ultimately, the sum of the required exit capacity cannot exceed what is available at each exit. You can't require more exit capacity than what is available. In other words, we have to make enough exit capacity to meet what is required. Additionally, no single exit can exceed 50% of the required exit capacity. Do I have to consider every story of the building exiting simultaneously? Well, yes, but you don't add occupant loads of multiple stories together. Even though many buildings utilize a total evacuation principle, where all rooms and all occupants evacuate upon the fire alarm activating, typically each story is analyzed individually for its egress capabilities. In IBC, Section 1005.3 addresses the required exit capacity for rooms, area, spaces, or stories, meaning each story is analyzed individually. The interior exit stair considers only one story, in other words, not all stories at the same time. NFPA 101 is even more explicit and states in 7.3.1.4 that only the occupant load of each story is used in computing the required exit capacity at that story. It also adds an extra bit, provided that the required egress capacity of the exit is not decreased in the direction of egress travel. That extra part is something called egress width continuity, which we'll discuss in a later video. So we look at each story individually. Why? If all floors are egressing at the same time and using the same exits, wouldn't there be a traffic jam in the stairs? Fantastic question. The premise behind looking at each story individually is that when the alarm goes off, occupants are in their respective rooms. They will first proceed towards the exit. Now, this is occurring on all floors simultaneously, so no one is in the exit yet. Once the first occupant of, let's say, the third floor reaches the interior exit stair, this is about the same time that the first occupants on the fifth and seventh floor have also reached the exit stair. Within those stairs, occupants will walk down towards the discharge floor. As those occupants are walking down, more occupants are entering the stair at each respective floor. Assuming all floors have similar occupant loads and similar furniture arrangements, the rate of people entering the stair is the same at every floor. The traffic jam actually typically occurs at the door to the exit stair due to the fact that, practically speaking, only one person can go through the door at a time. This controls the flow and thus ensures a roughly even evacuation. Now, evacuation times and egress simulations are outside the scope of this series. The takeaway here is that generally each floor is analyzed individually for egress capacity with respect to occupant loads on that floor. There is one notable case where occupants going down from an upper floor will meet occupants coming up from a lower floor. That is called exit convergence. It can affect the required size of the exit discharge door of a stair, but we'll cover this in a later video as well. So, say I have an occupant load of 70 people. Does my story need 2 exits? Yes, in the vast majority of cases. The basic answer is yes, and fundamentally it's important to understand when we have 50 or more occupants that we usually need 2 exits. But, like we said earlier, there are exceptions. Let's explore that. What IBC actually says is that all stories must have at least 2 exits or access to 2 exits. Okay. In order to use an exit, an occupant obviously has to have access to the exit. We already went over exit access. What's your point? The point is, this means you don't actually have to have an exit on your floor. You could go up or down a floor to reach an exit, meaning you could design a code-compliant building where the second floor of your building uses only open stairs, called exit access stairs, which are technically means of egress, but not exits. These aesthetically are far more pleasing than enclosed interior exit stairs. We'll cover this in greater detail in a future video, which differentiates between interior exit stairs and exit access stairs. So we have our fundamental understanding about the number of exits, but like so many parts of the code, we have exceptions. We love exceptions. Not every story requires 2 exits. There are specific and very limited instances where a story can have a single exit. These are severely restricted by occupant load and travel distance, meaning if there are very few people on a floor and the distance to the exit is really close, the code may permit there to be a single exit. You'll find these in the IBC, Chapter 10, Section 1006, subsection 1006.3.4, and finally in Tables 1006.3.4, parentheses 1, and 1006.3.4, parentheses 2. In NFPA 101, you'll find these in the individual occupancy chapters. These will be in the occupancy chapter, subsection .2.4. For example, in the IBC, in a business occupancy, a single exit on the first story above or below grade is permitted, provided the number of occupants does not exceed 49 and the maximum travel distance to the exit does not exceed 100 feet in a fully sprinkled building. NFPA 101 would permit a single exit for a new business occupancy with up to 100 occupants, provided the travel distance does not exceed 100 feet to the exit and the exit discharges directly to the outside. While this goes against the fundamental rule of always having 2 ways out, this provision permits a single way out in situations where the risk is very low. So, how do we determine the number of exits and the size of exits? The number of exits is primarily based on the number of occupants. More occupants means more exits. The specific size of exits required is based on the calculated occupant load from a previous video. There must be enough capacity in the exits to serve the occupant load. We use an exit capacity factor to translate the number of occupants into a required exit size. I'm Stephen Barrett. This is MeyerFire University.
This has been a preview of MeyerFire University. Join the next generation of fire protection experts at www.meyerfireuniversity.com.